In this next unit, we're looking at exponential functions. Part of working with exponential functions is being able to work with exponents. In grade 9, you would have been introduced to the idea of the exponent laws. And so in this first part of the lesson, I'm going to be asking you to see if you recall what those laws were and try to simplify some expressions. And then after that, we'll take them up. So the first part of this unit then is working with integer exponents. Right now, what I'd like you to do is see if you could take those expressions in the mind's eye and write them in a simpler form. Before I take these up, one thing to remember is that there's repeated addition and repeated multiplication. For an example, up here, I just want to write that 2a is equal to a plus a. That's repeated addition, so we use multiplication for that as a shortcut. It's a way of writing this much simpler. And then if we have a squared, that's a times a. So that's repeated multiplication. So in this case, the 2 means how many a's are being added together. And in this case, the 2 means how many a's are being multiplied together. And at this point, I'd like to remind you as well that these are terms. When they're being added, we call them terms. And these are factors when they're being multiplied. So those are some important parts to keep in mind as you work through this exponential unit. So looking here, we have, in this case, repeated multiplication. So that's 4 x's multiplied together. So we could write that simpler by putting an x and then a 4, rather than having to write all 4 x's. Here we have 2 a's being multiplied together and 3 b's being multiplied together. So that's a squared b cubed. Here we have 4 a's being added together. These are terms. So we have 4a. When we get down to these rational expressions here, one thing to keep in mind is the whole idea of reducing, and that a number divided by itself is 1. So in our rational expression unit, we talked about canceling. In these cases, there's actually canceling that can take place. There's all of these c's, and it doesn't matter which ones you pick, I'm going to pick the ones at the end. These cancel with each other. C times C times C divided by C times C times C, that's 1. So what we have is 1, 2, 3, 4, 5 C's left over being multiplied, so that's C to the 5. Now, the other approach we could have taken for this would have been to write these exponentially. So there's 8 C's being multiplied in the numerator and 3 in the denominator. And again, when we cancel 3 of the ones in the denominator would cancel 3 in the numerator, and that would leave 5 of them. And if you think about this, and you recall the rule for dividing powers with the same base, the operation that we use here makes sense when you think about canceling. So in this instance here, I can cancel those D's and those F's, and so I'm left with D squared, because these are 2 D's being multiplied, and F cubed. And finally, we have x squared over x squared, any number divided by itself. Remember, x represents some number, so when x is the same number in the numerator and denominator squared, that's just going to be 1. Next, what I would like you to do is go through this section of the action where it reviews the laws for working with powers of the same base and what to do with the exponents. And there's different situations I want you to go through and see if you recall how to do these or simplify them, and then what the rule would be. So as I mentioned earlier, exponents are really just repeated multiplication. So it's how many of the number, and in this case, a variable representing a number, how many of them are being multiplied. So basically, that's why we add the exponents, because we're just counting how many are being multiplied. So here we have 5x's being multiplied. Looking at B here, we have 5a's being multiplied and 3a's. So 5 plus 3, that's a total of 8a's being multiplied together. And then here, remember that because the number is, the exponent is referring to how many of the base, the value underneath, is being multiplied, you can only combine those that have the same base, because it wouldn't make sense to try to combine them when we're trying to talk about the same thing being repeated. So here we have the c, so we have to look at each of the c's and see that there's 6 c's, 4 plus 2, being multiplied together, and there's a 3 d's here being multiplied, and then here there's 1. Now, because it's just a d on its own, we don't bother putting an exponent. Remember, an exponent is to make it simpler to say how many we have, but it's clear to us that there is just 1. So we don't need an exponent, but we still have to keep that into account. When we're adding how many we have 3 d's and 1 d. That's a total of 4 d's being multiplied. So these are the simplified form of each of these expressions. And so the rule is, when you're multiplying powers, you add the exponents, because we're counting how many of the particular number or variable are being multiplied by itself. So we add the exponents. This next situation, we're looking at dividing powers. And this is a good time just to remind you of the terminology here. Thinking of x to the 4th, we call this whole thing a power. That's the name we give to all of that together. I'm assuming they do that because it's powerful, in that as you grow exponentially in terms of this number here, this exponent, the bigger that is, this grows much faster. And so these have 2 parts to them. This number that's being multiplied by itself is called the base. And it's at the bottom, so that would be a good reason for it. As well, it's kind of the basis of all of this. It's the base that we're working with. And we talk about number bases, whether we're base 2 or base 10 in terms of our number systems. We tend to work with decimal, which is base 10. It's based on 10. And then here we have an exponent. And so this is where we have this idea that we're dividing powers here. So, similar to the canceling that we did in the minds on, there's 4 x's being multiplied and 2 of them. Basically, 2 of these will cancel with 2 of those being multiplied, or we're subtracting the exponents because we're reducing the number in the numerator. So 4 minus 2 is 2. Here we have 8 c's in the numerator being multiplied and 2 in the denominator. 2 of these will cancel with 2 of those, so 8 minus 2 is c to the 6th. And remember that fractions are just a form of division. Notice how the division sign looks like a fraction. So c to the 6th divided by c to the 4. Again, we're dividing, we're subtracting the exponents, or we're canceling 4 of these c's with 4 in the numerator, or 4 in this dividend, this number being divided. And so we have c squared. And so in this case then, when we're dividing powers, the rule is to subtract the exponents. And again, that's because there's canceling taking place, so there's going to be fewer of them when we're done. Coming down to our third rule, a power of powers. Now, they do call them power of powers. I'm going to put a note in here because I actually prefer to call it a power raised to an exponent, just so people understand what's happening here. A power raised to an exponent. So basically we have a power and then we're putting an exponent outside of all that. So now in a sense the power, the original power inside the bracket is becoming the base. So this first one I'm going to just write out in a longer form. Remember that, say, when something's squared, you're multiplying that value by itself. So in this case, we're multiplying x cubed by itself. Now, thinking back to our rules and our exponents versus repeated multiplication and repeated addition, here, when we're multiplying, we've said that we add the exponents because we're counting how many x's are being multiplied. In this case, because the power is a base, what happens is we're also repeating the same thing over and over again, so the exponents are always the same number. Well, what we have then is basically, if this were to continue, let's say that was cubed or to the fourth or to the fifth, there would be more x cubes. We'd be adding 3 plus 3 plus 3 plus 3, which is repeated multiplication. So it turns out that when we have a power raised to an exponent, we can actually multiply these two. So you can see clearly here that 3 plus 3 is 6, but 3 times 2 is 6. So we have x to the 6. So in this next one, there's two ways to approach this. You could cube this whole thing first. So this 3 would apply to both of these exponents, and that's where you have to be careful to make sure that you apply this to both of these. This especially becomes a challenge for people when there's a number inside of the bracket being cubed, for example. Not just a power, but a number by itself. And it doesn't appear to have an exponent because it's just 1. And people will sometimes miss it. So one approach to this is to apply that 3 to both of these. So 5 times 3 is 15, and 3 times 2 is 6. And then add those together, 15 and 6 c's being multiplied is 21 c's being multiplied, or c to the 21. Now I'll just show on the side here the other approach we could have followed. We could have simplified the brackets first, so we could have added those exponents 5 and 2 to get c to the 7, and then all cubed. And then when you raise c to the 7 to the exponent 3, we multiply the exponent, so that's c to the 21. Looking at this last power raised to an exponent, these are both different bases, so I can't simplify the bracket this time. My only option is to apply this 4 to both of these factors within that expression. So x to the 2 times 4 is 8, and y cubed raised to the exponent 4 is y to the 3 times 4, which is 12. And so that's simplified. So the rule for power raised to an exponent is to multiply the powers. Multiply the exponents, I should say. Now, those are the main 3 rules for working with exponential expressions, where you're dealing with exponents and powers. Now there are some special cases we want to be aware of. The first special case is this situation. First of all, you may recall, hopefully, that 7 to the negative 2 is the same as 1 over 7 to the 2. The way I can illustrate that is to do an example with base 7 over here. So if I have 7 to the 3, all divided by 7 to the 5, we already know that this is 7 times 7 times 7, and then this is 5 7s multiplied. 3 of these in the numerator will cancel with 3 of those being multiplied in the denominator. So what we end up with is that cancels to be just 1, and then this cancels to leave 2 here. So what we have is 1 over 7 squared. Now, if we follow that rule, which we recognize is simply canceling where we said that we subtract the exponents, we could look at this expression here and we could subtract the exponents. And when we do that, 3 minus 5, that's more negatives than positives, so we end up with 7 to the negative 2. Both of these answers came from the same original question, and we agree that the rule works. Now, this rule where we subtract or cancel, this is easier to think about when we have more in the top than in the bottom, in terms of thinking of this idea of a 7 with a negative exponent. But what you want to do is first become comfortable that you agree that these must be equal because we followed proper rules, and then get used to the fact that really when you have a negative for an exponent, that's referring to an expression like this. And so it turns out that we can interchange the power from the numerator to the denominator by simply changing the sign of the exponent. So 2 ways of looking at this. The first way is adding the exponents, we get x to the 0. And here's where a question comes for people of what the answer to this is. Some people will say 0 because they see that 0 as an exponent, and that seems natural to them. Now, it turns out that the answer is something different. And if we take this question and we approach it the way that we were just talking about, so I'm going to take that x to the minus 5, and I'm going to write it in the denominator. Hopefully we've all agreed that that is fair to do. These are both the same question. Now what we have is the same number divided by itself, and we know the answer to that is 1. What that means is, similar to your needing to understand the idea of a negative exponent and just be willing to recognize that that's true, what we need to recognize over here then is that because these both came from the same expression, that x to the 0 is 1. Which leads us to the conclusion that anything with an exponent 0 has an answer of 1. So when we look at a situation like this where there's a negative in the denominator, I'm going to write this out in full just so we're all aware of what's happening. So when we subtract the exponents, it's 3 subtract the bottom exponent, which is minus 2. That's a 3 minus minus 2, which makes it positive, so that's 3 plus 2, and that would be a to the 5. So how does the rule for division affect the negative? Well, in this case, we're talking about the negative in the denominator. The negative in the exponent of the denominator became positive. Now, looking at C, it says write the result below as a power with a positive exponent. So, there's two approaches I'm going to show you for this. The one approach is to subtract these. So 4 minus 6 is minus 2. And then follow the rule that we just said that we can take that and put it in the denominator and make the exponent positive. Now notice, when I do that, if there's nothing in the numerator, I need to put a 1 there as the placeholder. The other approach to this, which is one that I'm going to suggest that we use when we're simplifying more complicated exponential expressions, is that if we want, we can think of, for example, canceling b to the 4 into the numerator and canceling b to the 4 in the denominator. That would leave a 1 in the numerator, and that would leave a b squared in the denominator. And that's pretty natural for us to think of canceling or dividing b to the 4 into the numerator and dividing b to the 4 in the denominator, or canceling b to the 4 here and canceling 4 of them down here. That would be 1 over b squared. So it turns out that if you start with the biggest exponent when you're dividing and you subtract and then leave the answer where you started, you'll end up with a positive exponent. So what I'm going to do is, in this case again, I'm going to leave 1 here because I am subtracting these two exponents. I'm dealing with these two powers. So 6 minus 4 is 2, and I started down in the bottom, right? I did 6 first, minus 4. That gave me 2, so I left my answer in the denominator. And so here are our two results that this is asking for. And those are all of the special rules that we need in order to work on these questions. Now, what I'd like you to do, based on those rules, this is actually a more involved. You can see here that these are not quite as complicated as this. I like to give this to my students just to get them thinking about how these could look. And the fact that ultimately, I want people to realize that if you know all these little rules that we just went over and you go through this very carefully and step by step, that's actually not as bad as it looks. I know the first time people do have difficulty with it, but I would like you to consider taking some time before you watch how it's done to try to do this on your own. It's always good. It says here group activity. It's always good if you have a chance to connect with some other people that you work with on your math. You could do that and see what they got, share your answers, etc., and talk about it before coming and checking for the answer. So at this point, I'm going to leave you to try this question. And in the next video, I will take up this example, and then we'll go through starting with some simpler examples, and we'll work through the application of those skills or those rules that we were working with originally, the exponent laws, and we'll apply them to the simplification of a variety of exponential expressions.